All right. So, as you can see, get a nice pen here. As you can see, we have this standard setup for formulae, like we've done with linear mechanics, rotational mechanics, fluid dynamics, all those wonderful systems in this course. And I just wanted to go through briefly with you each setup. This is voltage difference. It can be considered voltage drop if you go across a load or a resistor. Same idea, the idea that voltage is actually amount of energy used to move some charge. Um, we've defined it before in the unit breakdown. 1 volt is 1 joule per coulomb. So you have, again, energy and then the charge. So that's the amount of energy used to move charge, and that actually brings us to charge itself. We've discussed positives and negatives, not just protons and electrons, um, but there are other positively and negatively charged particles as we understand them as being positive and negative. There are, of course, neutral particles as well. And usually when you're talking about coulombs, it's actually a large number of these charges that we're discussing. So you'll have an example or two where you'll actually be asked, based on the coulomb value of an electron or of a proton, since they're basic units, you will actually use those to figure out how much charge is available in a certain situation. So for instance, a battery would have a certain amount of charge available to it based on the chemical contents. So then current, you see Q dot, it's basically just like V dot from before, the volume flow rate. Well, this is charge flow rate. So it's actually the amount of charge over time. So the unit of amps, I can give you another unit breakdown. It's going to be coulomb, a coulomb per second. This and this, very, very useful but simple conversions. So you can actually remember these sometimes better than you can remember the equations. Now with energy, extremely important, you have a voltage difference. Again, usually you consider it to be a voltage drop or the potential voltage difference if you use a certain load, and then multiplied by the amount of charge that that voltage would be used, or that the energy provided by that voltage difference would be used to move. So again, that's in joules. Extremely useful little equation here, sometimes known as the pi equation, okay, where E is the electromotive force and I is the current. And if you like, you can, of course, do this. You can cover up the E if you want to find, well, that's not going to work. Cover up the E if you wanted to find the voltage, and cover up the P if you want to find power, cover up the I if you want to find the current. So, to keep you from getting confused though, in case you're not familiar with that pi, this is just voltage. And again, change in voltage, voltage drop, same idea. And here it just assumes that you're using all the energy per charge. And then we've seen P equals E over T many times. Very, very similar usage as well. Just how much energy you use over the amount of time. And again, don't forget energy conservation. And soon you'll see something about Ohm's law, which is another simple relationship, very, very closely involved with the pi equation. And then we'll also look at something called Kirchhoff's law. Sometimes people call it Kirchhoff's or Kirchhoff's laws. You'll see why that is based on the spelling.